Okay, so hello everyone, and thank you for joining us today for another of our webinars. Today we are very glad we have with us Marija Tomasevic from the University of Barcelona, where she is a PhD student. Her research focuses around different aspects of the information problem of black holes and quantum gravity, and today she will talk about wormholes in general. So we are very glad to have you here, Marija. Thank you very much for accepting the invitation, and the floor is yours.
Thank you very much. And thank you so much for inviting me. I wish I could be there. As I told before, I've been to SISSA before and I really loved Trieste. But maybe in the summer, I don't know. But in any case, today I'm going to be talking about wormholes in general, as you said, but also about one specific aspect of traversable wormholes, which is about how time behaves within wormholes. However, to set the stage, I'm going to go through a little bit of a historical part and to just make. So wormholes, their solutions to general relativity have been known as, they're as old as black holes themselves. So the first wormhole was found just a couple of months after the first black hole, the Schwarzschild one, by Ludwig Flamm. However, today you might not know it as the Flamm wormhole. You might know it as the Einstein-Rosen bridge, which was rediscovered, so to say, in 1935. So one can see that wormholes are fairly old. And naturally, a lot of work has been done since then, both on the Euclidean and Lorentzian front. And so, for example, lately you might have heard something about some replica wormholes or some other wormholes that explain the late-time behavior of something called the spectral form factor, or even those that are discussed in the context of baby universes. However, all of these examples are not Lorentzian. And today we're going to be focusing only on the Lorentzian solutions. Okay, so to cover the basics, we have to say what general relativity is all about. General relativity allows for any smooth Lorentzian manifolds, as you know, to be a space-time. One simply has to solve for the right-hand side of the Einstein's equations in order to determine what is the stress energy tensor that is needed to produce such a geometry. However, not all of these geometries are going to be physically relevant. Some of them are going to be even pathological. And so we need to impose some restrictions on the types of stress tensor that we're going to allow within physics. And these restrictions are usually given in terms of energy conditions. So what kind of energy conditions we're going to be interested in depends on the type of physics that we're interested in. So for instance, if we are in the regime of classical physics, the weakest energy condition that we can impose is something called the null energy condition. It is simply stated in this form. It's just a stress tensor contracted twice by some null vectors, and this object has to be bigger or equal to 0. What this null energy condition basically says is that energy has to be positive locally. And we will see later why that makes light rays converge in the presence of classical matter. The other regime of physics that we might be interested in is quantum physics. And in quantum physics, we have something called the self-consistent achronal average null energy condition. So it's a bit of a mouthful, but the equation is not that complicated. It's very similar to the previous one, integrated along some null ray gamma. And in essence, it tells us that energy has to be positive on average along a fastest null ray. So let's go through these, all of these words that go before in the quantum energy condition. So the self-consistent part is there simply to tell us that spacetimes that we're interested in are the ones that solve Einstein's equation. So that's pretty self-explanatory. Then the important part of this energy condition, the important observation that was made not too long ago, is the achronality condition, which is the synonym for fastest. And its technical definition is that no points along a null ray can be connected by a time-like path. So for instance, if we take a two-dimensional cylinder where time flows in the upward directions, we can have two types of geodesics. The pink one is going to be a null geodesic, and the purple one is a time-like geodesic. And we see in this example in particular that the pink geodesic, the null one, is not the fastest one, since there exists a shortcut in terms of this timeline geodesic. And therefore this pink one would be a chronal, not achronal, but chronal. So not fast. Okay, so that's the second thing. And the third thing that we have is the average part, which is also pretty self-explanatory. It simply exists because quantum fluctuations are known to lead to locally negative energies. And so if we would want to have some sort of an energy condition, we want to average over those locally negative contributions in order to get on average a positive contribution. So that's the quantum energy condition. And so I said before that we can use these energy conditions to depict how light rays behave in the presence of some matter, be it classical or quantum matter. And we do this by using the Wright-Chuduri equation. And since we're interested in the null geodesics, here I've written out the Wright-Chuduri equation for the null geodesics in 4 dimensions. So the important part of this equation is this theta, which is the expansion scalar. It's basically the rate of change of the area, the cross-sectional area that null geodesics wipe out as they're moving. And we see that there is this object here that we already saw in the null energy condition that plays a role in this equation. And so for instance, we see that if our null energy condition holds, aka we're in the regime of classical physics, we see that the derivative with respect to the affine parameter has to be less than 0, because this is positive and these two things are squared, so the whole thing has to be negative. In other words, we have positive energy focusing light rays. So this is something that will occur near any massive object or any object that is classical, so to say. For instance, if you have a black hole, you know that light rays are going to be converging near it, or just by any star or any object that has enough gravity around it. But if we have positive energy focusing light rays, then that must mean that negative energy can defocus light rays. And that's really true, because since the only thing that we need then is for this object here to be negative enough, well, positive enough, to say, to overcome the effect of these two first factors and to overturn the derivative of the equation. Okay, and now we can use these energy conditions and the Wright-Chuduri equation in order to classify the set of allowed wormholes. And the way we can do that is by looking at the geometry of a wormhole. So let's see how we can do that. Here is the usual stock image that you can find on the internet for a wormhole. And let's say that we want to consider a traversable wormhole. So we want to go from, let's say, up here in the wormhole, through the wormhole and down. We want to exit. And we want to see what this situation is going to imply for our expansion scalar. So as we're starting, the expansion scalar is going to be negative, which means that the spheres that are initially big are going to get smaller as we're moving towards the bottom of the throat. However, when we get to the bottom of the throat, we see that we have to overturn this derivative in order to exit to the other side. Or in other words, our light arrays that were initially converging, for us now to traverse through the wormhole, they have to be defocusing and diverging. And in order to diverge, they have to, so to say, violate the Wright-Chuduri equation. And so if we manage to overturn this derivative, we get to the other side and the expansion is again positive. And so now we can deduce something about these wormholes with respect to what regime we're in, classical or quantum. In particular, we see that classical physics is going to forbid traversable wormholes. Why? Because classical physics, as we've seen, has to obey the Wright-Chuduri equation in which the derivative is always negative, which is clearly not the case here if we have a traversable wormhole. However, we know that quantum physics allows for negative energies, and therefore quantum physics can allow for traversable wormholes. So that's the basic argument. However, there does exist one caveat. And the caveat is that the wormhole that we're considering has to be long. And the length of the wormhole is connected to the achronal part of the quantum energy condition that we discussed before. So let's go into a little bit more detail about why we need long wormholes. So here is an excellent depiction of what a wormhole looks like. And here we'll be interested in these two light rays, one going through the wormhole and one going through the ambient spacetime. So if we want to traverse through the wormhole, we see that the average energy, null energy, has to be violated along this geodesic. In other words, since we need negative energy to support the wormhole, we're going to not have on average positive energy. But that's fine because that's not the only thing that we care about. We also care about our energy condition having the achronal part in it as well. As you might recall, achronal means that there exists a shorter time-length path. So that's why we have two geodesics that we want to compare. So if we were to have a short wormhole, this blue geodesic would be the shortest way to get from point A to point B. It's a short wormhole and it acts just like any other science fiction-y wormhole would act. However, that would mean that this blue geodesic is an achronal geodesic, and therefore our quantum energy condition would be violated along it. However, if this wormhole was to be long, and this blue geodesic to be longer than the green one, then it would take shorter amount of time to go along the green geodesic, and our quantum energy condition cannot apply anymore to the blue geodesic. So since long wormholes have chronal geodesics, we don't get any violation of the quantum energy condition, or in other words, the SKNEC. It's, I guess I'll be using them interchangeably. Are there any questions? Okay. So just a quick summary. We see that classical physics allows for non-traversable wormholes, but quantum physics allows us to have long traversable wormholes. Okay, so this was like the theoretical part of the of wormhole physics, but can we actually have some examples of how this would work out in practice? And we have many different examples. And for instance, starting with 2016's Gao, Jeffers, and Wall, now pretty well known. Gao, Jeffers, and Wall managed to construct a short-lived traversable wormhole within the context of ADS-CFT. A couple of years later, Maldacena and Chi managed to construct a long-lived traversable wormhole, also in the context of ADS-CFT. Then in the same year, we had a set of papers that managed to go outside of the ADS-CFT framework and construct wormholes in a perturbative fashion and non-perturbative fashion by using cosmic strings or magnetic fields. We're going to be going into a little bit more detail about this magnetic field wormhole in just a second. And I would just like to mention that there exists an upgrade to these wormholes where we can now have humanly traversable wormholes by putting them on something called the Randall syndrome brains. We can talk about that a little bit later. So these are just a couple of examples that I put here to highlight what's been going on in the last couple of years. Of course, there are many other examples, but this pretty much sums up the big things. So let me go into a little bit more detail on one of these examples. So this is going to be just one slide, so to say, show. And this is traversable wormholes in 4 dimensions that were constructed by Maldacena, Milekin, and Popov a couple of years ago. So the basic picture is something like this. And what Maldacena, Milekin, and Popov did was to start with 2 magnetically charged Rising-Earths and black holes in asymptotically flat spacetime in 4 dimensions, although that's not a restriction. And they managed to connect them by a common throat. So you might recall that Rising-Earths and black holes in the near horizon limit, they're going to develop a throat. And that throat is infinitely long or finite, depending on your level of extremality. And it's described by ADS2 crosses 2 geometry. And in particular, it's described by Rindler ADS2, because we need the horizon, it's a black hole. However, if we have 2 of these magnetically charged black holes, we can connect their throats by using the global ADS2 representation. And so that's how we get a wormhole. Well, that's how we get a wormhole geometry. We still need to support it with some negative energy, as we discussed in the beginning. And for the traversability, they utilize the magnetic field lines that come from these magnetically charged black holes that also thread through the wormhole. And they put fermions, basically electrons, to go on a loop around these magnetic loops, providing this negative Casimir energy. So this is a known calculation that one can do in ADS2 spacetime. And this is what they use in order to make the wormhole traversable. However, their paper was bound to, their paper was using standard model physics, basically, coupled to gravity. And so since they were willing to stay only within the restrictions of standard model, they had to impose some limits on what the size of these wormholes is going to be. And in particular, these wormholes ended up being very small, of the order of the electroweak scale. However, they are still traversable wormholes. And not only that, they're also long-lived wormholes. One can send small, not too energetic particles through the wormhole a couple of times before the wormholes collapse, so to say. So they're pretty well established. And as I mentioned before, one can make an upgrade of these wormholes by making it humanly traversable. And the way they have done this is by embedding the solution in a 5-dimensional bulk. So what we do is we have a 5-dimensional ADS spacetime, and we put a brain inside of it, which is 4-dimensional Randall-Sundrum brain. We put the solution on the brain, and then instead of these fermions providing the negative energy, it will be the holographic CFT coming from the 5-dimensional bulk that would support the wormhole with its massless so-called dark sector. So it's a pretty neat construction, and they managed to make it within the bounds of what an acceptable Randall-Sundrum brain constructions allow. So they truly can be humanly traversable. Now, that's not the only upgrade one can do. One can also generalize all of these examples in various different ways. For example, in a paper from not too long ago, we managed to construct a multimouth traversable solution by simply inserting a small black hole at the bottom of the throat of this original Maldacena Limpopo wormhole. So we were just inserting a small black hole that would have its own throat, and that throat would connect to the ambient spacetime, thereby creating a multimouth construction. That's not the only way one can make a multi-hole. There was another paper around the same time that made a multi-boundary version of Gardner-Jeffers wall. So this would be in 3-dimensional PTZ kind of setting. So now you might wonder why making multi-mouth wormholes would be useful, except for the purpose of simply creating new solutions. Well, one of the interesting aspects of having multi-mouth traversable wormholes is that one can then study the multipartite nature of entanglement from the dual theory. Of course, this is all in the context of ADS-CFT. So you might have heard about the slogan of ER equals EPR, but this slogan, as well as its whole field of study, is very bipartite in the sense that it only uses 2 systems and therefore 2-mouthed wormholes. However, entanglement in its essence is a concept that is multipartite. And therefore, if one was to study proper properties of entanglement structures, one would need to examine its multipartite nature. And therefore, these solutions can be useful for this. And in fact, there has already been some previous work that identify a way to determine this structure by simply looking at positions of certain surfaces, so-called extremal surfaces. In essence, if one imagines a wormhole, you would look at the surface inside a wormhole of the smallest area and compare the distances between these surfaces of smallest areas. And so by comparing their distances, you can see if the entanglement structure is one way or the other. For instance, if the surfaces are all similar in the distance to each other, that would indicate, if there's 3 mouths, a tripartite entanglement structure. And if some distance is closer than the other, then that would indicate a more bipartite nature with some tripartite entanglement structure and so forth. So that is the basic idea behind their way. However, what they did was for wormholes that are non-traversable. And so there is room here for a project that one can expand to traversable cases as well. Okay, so enough about generalizations. We want to see also if there are any pathologies exhibited in these wormholes. We have so many examples, but are there any ways that we can make these examples pathological? And why might we think that? Well, if we have something that allows us to travel to faraway places, it also allows us to travel to faraway times. And one might wonder if this can allow us to travel even back in time. And indeed, before 2016, people were working with various toy models of traversable wormholes. So the way to utilize the negative energy coming from the Casimir effect wasn't still figured out quite. So people were using simple exotic matter that would have all the necessary ingredients of providing its negative energy and so forth that would support the wormhole. And that's how they managed to have toy models of traversable wormholes. what this exotic matter actually was didn't really make any difference. However, in these toy models, they found out that if we have a traversable wormhole, it would seem very easy to try and make a time machine out of it. And in fact, it seemed so easy that they saw that it might be a generic fate of all traversable wormholes. So this is work that has been mostly explored in the 80s and the 90s. And people really, really investigated these models, and they really saw that this is going to be a generic fate of all traversable wormholes. So let's see how this might happen. What is the recipe to create a time machine out of a traversable wormhole? Well, first we need a traversable wormhole. Then we need to induce a time shift between the wormhole mouths. That means to induce a time delay or advance of one mouth with respect to the other. And in the end, we simply bring the wormhole mouths close together. So that's it. That's the whole recipe one needs to have in mind. So I want to go into a little bit more detail about all of these steps. Step number 1, I think, is pretty covered given this talk. Step number 2, we have to induce a time shift between wormhole mouths. So there are various ways one can do this, but the simplest two are that we send one of the mouths on a twin paradox-like trip, or we can simply put a massive body next to one of the mouths. The point here is to rely on special or general relativistic time dilation. Then going through the wormhole would connect you to different times, one here and one there. And in particular, if we were to put a massive object next to one of these mouths, the gravity of this massive object would slow time near one of the mouths so much, it would slow it down so that the time difference between the ends of the wormhole would gradually accumulate. So that's step 2. We have to accumulate the time shift. And finally, step 3 would be to bring the mouths close together. And now you might wonder, how close do I have to bring them together? Well, until the time it takes us to go from and to one of the mouths is shorter than the time shift that we have induced. In order to give an intuitive picture of what's going on, suppose that the time shift was 5 years. Then we can have one astronaut passing the wormhole in one direction, and he would jump 5 years into the future. However, another astronaut passing in the other direction would jump 5 years into the past. And if he returns to his starting point by high speed across the ambient spacetime, then the second astronaut can get back home before he even left. That's a closed time-like curve. In other words, closed loop in space would become a loop in time just as easily, and we would really confuse our astronaut. So this doesn't seem very sciencey, so to say. Physicists right away started to work on these problems. And throughout the years, they managed to come to 4 different levels of resolution, so to say, which I'm going to list now from the least radical to the most radical, so to say. So the first option that people came up with is that traversable wormholes simply do not exist, and therefore we do not have these pathologies. The second option is that they do exist, but time machines don't exist. Why? Well, some quantum gravity effects are going to prevent the time machine from forming. The third option is that both are allowed, but time travel is self-consistent, so you would never encounter any sort of grandfather paradoxes of any sort. And of course, the fourth most fun, I guess, option is that everything is allowed and radical new physics is necessary. So given this talk, I think it's safe to say that the option number 1 is not correct. So we're going to go to option number 2, which we will argue eventually that it is the correct option in some sense. So this second option uses traversable wormholes, but doesn't allow for time machines. And this is nicely summarized in Hawking's chronological protection conjecture. It basically says that we have traversable wormholes, but quantum gravity effects are going to kick in before we ever form the time machine. And so why quantum gravity effects? What led Hawking to actually postulate this part of the conjecture? Well, he was supported by several calculations that have been done in wormhole spacetimes that seem to indicate that there is a divergence of a quantum stress tensor at the boundary of the chronology violating region. So chronology violating region is basically where all the closed time-like curves exist. There is a boundary that separates that region from the region that is completely regular. And the reason why it's a quantum stress tensor is because we needed to use quantum field theory on curved backgrounds. And since we have a divergence of a quantum stress tensor, well, that indicates some sort of quantum gravity effects becoming important. And that's how he got to a conclusion that quantum gravity effects are going to kick in before we can cross to this other closed time-like curve side of the spacetime. Okay, so that conjecture was made 30 years ago or so. So what is going on today? Today, we have these time machines that are still stuck in this conjectural limbo, which prompted me and Roberto to work in progress, really is still in progress, to try to tackle these problems of time machine formation from two different perspectives. So this resulted in two different projects. And the first project is about the chronology protection conjecture itself, where we argue that it does hold, but it does not require really quantum gravity. Our goal is, of course, to show that one cannot make a time machine out of a traversable wormhole, but that instead of quantum gravity effects, the wormhole will simply back react in such a way that the time shift will never become bigger than the distance between the mouths, therefore never actually forming a time machine. We have a complementary project where we allow for time machines, so to say, and we want to investigate what happens if one embeds them in ADS-CFT. So we want to see what is a holographic dual of a time machine spacetime if we put this time machine on the boundary of ADS. And we simply look at what happens in the bulk. And our preliminary results indicate that the bulk is going to be regular until the chronology horizon, as you might have expected. But then it seems to form a hole of some sort. In other words, it becomes geodesically incomplete. And this is not something that we understand fully. So one might have expected that if I have a pathology on the CFT side, that I will have some sort of a divergence in the bulk of some sort. But here it simply seems to develop this geodesic incompleteness. However, given that we don't fully understand yet what are all the consequences of this geodesic incompleteness, I'm going to be focusing on the first project. Okay, so let's review the basic argument behind this project. One of the reasons why wormholes provide an apparently easy way to form time machines is because of these closed loops that are non-contractible, right? We have some non-trivial topology and we cannot contract all the cycles, so to say. However, the same inherent structure cannot be supported without obeying certain energy conditions. That is the one that we were mentioning in the beginning of this talk, the scaneck, or the quantum energy condition. And we saw that this energy condition already restricted the set of all allowed wormholes by restricting their length to be longer than the ambient space distance. And so if it already restricts the inherent structure of a wormhole, one might pose a question that if we can use this energy condition to restrict time machines as well. And to be fair, this has already been done to some extent in these papers that are noted here. However, what these papers have done is simply show that the energy condition that we're using is incompatible with time machines. But these papers don't tell us what really goes wrong if one tries to follow through the recipe that I mentioned and tries to form a time machine. So this is what we want to explore in this project. So recall, the quantum energy condition, or the scaneck, is applied to a null geodesic, which represents the shortest path between wormhole mouths. And as I mentioned, this is the reason why only long wormholes are allowed, since the scaneck then applies only to the exterior distance and we don't have any problems there. But in a setting when we are inducing a time shift, which is our setting, and when we are slowing down time at one of the mouths, we are effectively prolonging the ambient distance between the mouths, or in other words, effectively shortening the wormhole length. And if we are shortening the wormhole length, Well, that means that in this process of making a time machine, at some point, we're gonna hit that wall, so to say, and first make the wormhole the shorter path, thereby violating the energy condition that we started with in the throat. Is this clear? If there are any questions, this will be a good time to ask. I'm going to cover now in more detail how we get to this result, but this is the basic logic behind the argument. Okay, so notice that we're making the wormhole shorter, aka the ambient distance longer, only in the sense of how much time it takes to traverse it, and not literally by shortening or elongating it. And I mean, regardless of the statement, the scaling applies to the one geodesic which takes the shortest amount of time. And therefore, if we do make the wormhole even effectively shorter, it's going to violate this quantum energy condition. And know also that this quantum energy condition is a semi-classical energy condition. Semi-classical, I mean gravitational equations are satisfied and quantum matter is allowed. And so if we violate this semi-classical condition, well, that means that the prevention of the time machine formation is kicking in before any quantum gravity kicks in. We're still in the regime of semi-classical physics. Okay, so I've laid out the basic argument, but now we can go and be more precise. So let's go back to our favorite picture of the extraordinary wormhole. In order to be more precise, I want to set the notation and be very clear with all the T's and the D's that we'll be using. So we will denote the proper time for exterior observers by big T and the one interior with little t. We'll denote the exterior distance with d and the wormhole length by L. So these are always going to be our relevant parameters of these geodesics. Now, since we're going to be using some time shifting, we need some parameter to track this time shift, and we need it to track for each mouth separately. So we introduce phi, which is basically the gravitational potential, as you can see here. The wormhole time is connected to the exterior time simply by rescaling with the gravitational potential, and they can be different and at different mouths. So this is something that we're going to see have effect when we bring, for example, a massive body next to one of the mouths in order to induce a time shift. However, in the beginning, of course, all the clocks are synchronized and our gravitational potentials are equal in the beginning. Okay, so what does inducing a time shift mean? It means putting a massive body next to one of the mouths, say mouth 1. And so if we put a massive body next to one of the mouths, the effective mass of the whole system increases, thereby decreasing the gravitational potential. And so we have induced some sort of a gravitational difference, gravitational potential difference. However, this is not enough to make a time machine. So how can we do this? Well, we'll see that in order to achieve a closed timeline curve, so to say, we have to enter the heavier mouth, go through the wormhole, and exit through the lighter one, and come back before we even started, which is going to be allowed only if this phi 2, so this potential at the second mouth, is going to be large enough. So let's see how this is going to work out, this little paragraph that I just said. And in order to get some intuition, we're going to do this analysis for zero-length wormholes first. So zero-length wormhole means don't look at this red tube. And so we can go slowly through the argument. So when we enter the first mouth at some exterior time, big T, which translates in the wormhole parametrization to small t, which is rescaled by this gravitational potential, then since the wormhole is zero length, we immediately pop up to the second mouth, mouth 2, which the parametrization then changes to this exterior time t prime. It's now different. If these times were the same, if there was no time shifting, phi 1 and phi 2 would be the same, and therefore we would not have any difference. But we do have difference because of this massive body, and therefore our t prime is different by this rescaling of the gravitational potential difference. Okay, so when is a time machine formed? Well, it's formed when two conditions are satisfied. First, this time has to be smaller than the original time. This is because we simply want to go back in time and meet ourselves, if you will. But that's not enough, because the time shift that we induced has to be also bigger than the distance between the mounts, because we want to get there faster than what it takes us for the distance to, cross, actually. And so this can be written in this way. So using these two conditions, we can arrive at the critical time when our time machine is formed, which is given by a very simple formula. So this is T critical. D is the distance between them, and this is the difference in the gravitational potentials. And actually, we arrive at a very similar condition, even if our wormhole had a finite length. The condition would look like this then, in that case. So it's simply, we just add another L to it. So I haven't gone through the detail of how one would do for this finite length scenario, but it's very similar to the zero length one, so one can try to follow through. And because of this condition here, we see that this common law, which was stating that time machines can only occur in short wormholes, is wrong. This length of the wormhole can be just as large as we want, and the time machine is still going to form. It's just going to happen sometime later. Okay, so we have our time machine formation time. So what about the quantum energy condition? So we want to see when the exterior light ray, this green one, arrives later than the interior one, thereby making the wormhole a shorter path, and thereby violating the quantum energy condition inside the wormhole. In order to see how this happens, we impose a race. And we start the race at some exterior time, t, as before. So it's after the mouths have gone out of sync. And we shoot out two light rays, one through the wormhole, the blue one, and one in the ambient spacetime. And now we simply have to compare what are the times when these light rays come to this mouth too. So for the first light ray that goes outside, it's simply some time that was already induced, plus the distance the light ray has to cross in the ambient spacetime. And as for the inner light ray, we see a similar logic as before. So this phi2 here is because of the second mouth. We're going to exit through the second mouth. And this t prime is simply L plus t. L as in the whole length of the wormhole, and the t that comes from this out of sync time shifting that we've done, which can be rewritten in this way. And so now that we have our times, we can see when the quantum energy condition is going to be violated. So simply when this time is bigger than this one, which translates into another very simple condition for the critical time. So this is TA, the critical time for the violation of the quantum energy condition. And if you remember, the time machine formation time was given by this formula here. And now we clearly see this, that the time to violate the ANAC is shorter than the time to create the wormhole. It happens before that. And the ANAC gets violated before we even start thinking about a time machine in these usual settings. Okay, one might wonder if this was too simple. We basically confirmed our intuition on these toy models. But if you remember, these toy models were the ones getting us into trouble in the first place, giving us all these pathologies and so forth. So one might wonder what happens to the actual solutions that we have already, like the ones in Multimouth, like in Popo, or others. Well, we started doing this calculation, and we have some preliminary results. In the wormhole of Multimouth, like in Popo, one finds sort of a dragging effect in the wormhole that stems from this additional massive body that we have put next to one of the mouths. And this dragging effect is important because it goes in the opposite direction to the time shift, thereby effectively elongating the wormhole again and never allowing it to surpass distance of the ambient spacetime. In other words, the solution seems to be self-correcting, never leading to any quantum energy condition violation, and thereby never even coming close to a time machine formation. However, we still have some kinks to work out and to dot all the I's and whatnots. So, but it will be published soon, I hope. So let me then finish with a little summary. We see that traversable wormholes are now understood much better than before, and we know what type of physics is necessary for their existence. We need negative energy and we need long throats. And it's not just the theory part that we know. We also know how to construct various different examples that are parametrically controllable with 2 or more mouths within and outside the framework of ADS-CFT. And we now know that these previously found pathologies regarding wormhole time machines are incomplete in a sense. Hawking's chronological protection conjecture is true, but there is no need for quantum gravity resolution. Semi-classical analysis is good enough to show that no wormhole can be turned into a time machine. Thank you.
Thank you very much, Maria. It was a very interesting talk, and now we have a time for questions. Yes, if anybody has a question, please unmute yourself, and you are free to ask.
Okay, I have a maybe naive question. What if we have a time machine? Does it mean the energy conservation will break down? I mean, if the energy conservation is in a closed system, the d over dt is it's equal to 0, right? But if one particle or elephant come into a wormhole and it just disappear, but it will appear in another place or another time, so the energy is not conserved. I'm not sure.
So yeah, you are right in the sense that we have, so the phi's that I was mentioning before, they lead to non-potential fields. So that's the one way that you can think about it. But we are arguing here that time machines are never going to exist anyway. And I would say that if you had time machine, energy conservation would be the least of your troubles. But you were right. So the non-potential fields here can induce this type of physics. But you're not going to lose any information, so to say. Everything is still there. So information content is still preserved. I don't know if I answered the question.
Because I'm not familiar with this field, I just think it's an interesting topic.
Thank you. It is an interesting topic. I think so as well. But yeah, just wormholes on their own are completely fine. The time machine aspect is the one that would induce you these troubles, including the non-potentiality of these gravitational of gravitational field. Yeah.
Okay.
Okay. Do we have any other question?
Yes. Hi. Very nice talk. Thank you. Yes, I was wondering, how would you build one of these traversable wormholes? Like, is there any kind of realistic way of doing that? How would you go about it?
Depends on what your definition of realistic is. I guess if you are in the regime of really theoretical physics, then everything is as realistic and you can just pop them out from the gravitational path integral. So that's something that people use. However, there have been some talks about how maybe one could try to build a traversable wormhole by, in some sense, just putting 2 mouths very close together and then allowing for some non-perturbative physics to happen and connect the throats. If you remember this example of Melusine, Milekin, and Popov, they had these 2 black holes that in essence are black holes just connected by a common throat. So you might wonder about a dynamical process of like bringing them close together and then somehow connecting them. But this physics hasn't been worked out completely yet.
But it would be possible with just the fields of the standard model. You wouldn't need to introduce new quantum fields to be able to do it.
You would definitely need to introduce, even in the standard model picture, you need to have a lot of flavors of fermions in order to support the wormhole. So you have to have a large number of quanta to support the wormhole. Now I would assume that in order to create it, you would also need a very large number of quanta, at least these new fields. But how new do you have to go? Do you have to go very beyond the standard model or not? That I'm not familiar with.
Okay.
Yeah, but as I said, you can make this through a tunneling of some sort. And just imagine two black holes popping out of the vacuum, and then creating a wormhole that's traversable. There are also papers on this topic as well. So I can give you a reference if you want.
Cool.
Yeah, it's by Merolf and Horowitz. It's a paper called Creating a Traversable Wormhole. So if you were to type...
Yeah, could you put it in the chat?
Yeah, of course. Should I stop sharing, I guess?
As you wish.
Yeah, I guess I can come back just to find the paper and put it in chat.
Yeah. Okay, while you type, if there is any other question.
Yes, I might have one.
Yes.
So it's a basic one. So when you talk about this Skyneck, and you say, okay, so we need long wormholes because in that case, the green time-like path is shorter than the blue null path, right? But I just try to understand this statement because like whose clock are we talking about? Like when we measure their time distance?
These are always asymptotic, so it's not proper time.
So some asymptotic observer,
right?
It's coded, but does it matter? Like if I do a boost or something like that, then it changes the time reading, so to speak.
I mean, you can do this twin paradox like kind of trip if you want to induce this time contraction. This would induce for you the time shift. But
okay,
you should always consider just, yeah, these asymptotic times. Because in proper time, for example, the time to go through, it can be seconds if you want. For you to get
right. So I just try to get, I mean, because the way you talk about it, you know, one longer than the other seems to be an invariant notion that it's sort of frame independent, or do you actually mean it's a frame dependent statement? Because you're not talking about proper time now, right? So it's really some coordinate time. So when you talk about coordinate time, I'm just a bit worried whether it's a sort of a coordinate dependent statement that, you know, the blue one is longer than the green one.
Well, in some sense, it's coordinate dependent, but for all asymptotic observers within that coordinate system, this is going to be the case.
Okay.
Yeah, okay. So that's the point. Because you have to integrate over the whole geodesic. These geodesics don't stop there. They go to infinity, so you have to take care of that. It's non-local in that sense, but
I see. Okay, so they're coming from infinity to entering one of the hole and then leave through the other hole and to the and back to infinity. That's the picture.
Correct. Yeah.
Okay. Thank you. Yeah.
Thank you for your question.
Okay. Somebody else? Okay. If not, I have a question myself. Okay, everything that you have talked about, in particular the last part about the violations of the conjecture, is by assuming that these black holes are stable, right? But the simple solution probably to the problem of time machine is just that these black holes are unstable. So in the moment you attempt to cross them, the throat just collapses because your presence there. So
well, that depends on the energy gap. So these solutions that Maldacena, Milekin, and Popo constructed, the original ones, have such an energy gap that they allow for small things to cross. And by small, I mean not too energetic. You can also do this humanly traversable, but you can still cross and not collapse the wormhole, even within this, at least perturbatively, it looks like you wouldn't collapse the wormhole once you try to make the time machine. But this thing goes in this other project that we're still working on with the preliminary results of the dragging effect. So what we're seeing is this, if you will, TTR component of the stress tensor that seems to go in the other direction. But we see also that the length is getting elongated of the wormhole. So that's why I was saying that it seems to be self-correcting. But I think you're right that in a sense that maybe non-perturbatively it can even lead to a collapse of a wormhole. So that can also be some sense in which this wormhole would be self-correcting.
Okay. Yeah, and by not very energetic, you mean like, I don't know, sending electrons, but no way sending a person, basically. No?
Well, if you were in this Randall syndrome setting, you can send a person. But in these wormholes that we were working with, yeah, it's just electrons.
Okay.
Yeah.
And he asked a funny question, which is more science fiction than science, but okay, imagine that these objects are out there in the universe, okay, that whatever, they are natural or created by some alien civilization, whatever, and they are being used to travel. Is there possible that they could emit, I don't know, a signal on gravitational waves when you cross that you could distinguish once we have a good gravitational wave observatories in the future? Something, or they just look black holes for the outsider?
So from the very far away, it really looks just like a black hole. So I wouldn't say that there is any way to distinguish it. Okay. Of course, if you send a signal and it can pass through, it can go through the other side, you're going to see something funny going on with that black hole. But from afar, just if you look at it and if you try to use some simple probes, I don't think you can distinguish it from a wormhole very much.
Okay, thanks.
Yeah.
Okay, so I don't know if there is one last minute question. Otherwise, thank you very much for your talk. It was very interesting.